Today we're discussing J.J. Thomson's discovery of electrons and how Millikan used that knowledge to conduct his oil drop experiment to test the charge of electrons. Let's get started. In 1897, J.J. Thomson discovered the electron and measured its charge-to-mass ratio using the cathode ray tube experiment. Thomson and others tried to measure the charge of an electron using clouds of charged water droplets. They observed how fast the water droplets fell under the influence of gravity and an electric field. In 1909, Robert Millikan began experiments to determine the charge of an individual water droplet rather than measuring the whole cloud of water, but found that droplets of water evaporated too quickly for accurate measurement. He then asked one of his graduate students, Harvey Fletcher, to find a material that would evaporate more slowly. Fletcher found that droplets of oil dispersed by a simple perfume atomizer injected into an air-filled chamber would pick up the charge from the ionized air. Through a microscope, the droplets were observed while an electric field was applied to the upper and lower plates of the chamber. By measuring the time and velocity for the droplets to fall or rise and applying Thomson's charge-to-mass ratio into an equation, Millikan could calculate the charge on the drop and therefore the charge of each electron in that drop. Millikan won the Nobel Prize in 1923 for this work, as well as the determination of the value of Planck's constant in 1916.
British physicist J.J. Thomson had measured the ratio of electrical charge to the mass of an electron using a cathode ray tube in 1897. Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to NE, where N is equal to 1, 2, 3, and so on. Using the value of charge of the electron, the mass of the electron, ME, was then determined by combining Thomson's value of E by ME ratio. The value shown is the value of the mass of an electron.
Hey everyone, this video is on Millikan's oil drop experiment. Millikan's oil drop experiment determined the charge of an electron. His experiment involved the manipulation of electric fields only. This diagram is a simple representation of Millikan's apparatus. A chamber is divided into two parts. The first part, which contains oil droplets produced from an atomizer. The second chamber, at the bottom, involves the application of ionizing radiation and electric fields where the top plate is positive and the bottom plate is negative. In the top chamber, oil is atomized into individual droplets so that they can be analyzed by Millikan. When an oil droplet falls through into the bottom chamber under the influence of gravity, X-rays are used to ionize gas molecules by knocking out their electrons. These electrons from gas molecules are then donated to the oil droplets that manage to fall through into the second chamber. When oil droplets acquire these electrons, they become negatively charged. For example, if an oil droplet acquires 4 electrons, then it will acquire the charge of exactly 4 electrons.
What if we could adjust the voltage so that it is just right? And by just right, I mean that we find a voltage number where the upwards electric force on the droplet gives exactly the same amount of pull as the downward gravity force. Okay? So if the voltage is a little too high, the electric force is going to be bigger than the gravity force, so the drop moves up. If the voltage is a little too low, the electric force is going to be smaller, so then the gravity force wins and the drop moves down. But if we get the voltage just right, the drop isn't going to move up, it's not going to move down, it's just going to float in midair. And that's because the electric force and the gravity force are both pulling, but they're pulling the exact same amount. It's like two teams trying to play tug of war, but both teams are equally strong, so they can't move the rope in either direction. So when the electric force exactly equals the gravity force, the oil drop is just going to stay still. When this happens, electric force equals the gravity force. This is a very important situation, and it's what the people doing the experiment try to do. They adjust the voltage looking at a single drop until they can get it just right so that the drop stays still. Now, for each drop, they do this with many different drops. For each drop, they find a way to determine the mass of it, how much it weighs. So for this one, let's just say you write the mass down, and then they write down the voltage at which it balances, staying still. And they do this for many different drops. They do it for many different drops of different sizes.
So the question is, how did Millikan determine the mass of each oil droplet? Millikan did this by switching off the electric field. When the electric field is absent, the oil droplets will be subject to the weight force and also air resistance going upwards. When the magnitude of the weight force equals to the magnitude of the drag force or the air resistance, each oil droplet will be falling at what we call a terminal velocity. This is when the oil droplets are falling at the greatest velocity possible and at a constant speed. The terminal velocity, when measured, gives information on the volume of each droplet. Given that the density of the oil is known to Millikan, the mass of each droplet is calculated by timesing the density of the oil that's used by the volume of the oil that can be calculated by using the terminal velocity of each droplet. Afterwards, the mass of the droplet can then be used to calculate the charge of the oil droplet as we saw previously. Millikan repeated the calculation of the charge of an oil droplet many times for different oil droplets, and he recorded the charge of each droplet. This graph shows you an example of his results. Millikan realized that the charge of the oil droplets are all quantized, meaning that the value of the charge were all multiples of a very small value. Millikan found the value to be minus 1.5924 times 10 to the power of minus 19 coulombs. Millikan interpreted this quantization of the charge of the oil droplets to be due to the discrete or the specific number of electrons that were suspended in each oil droplet. He proposed that the total charge of the droplets depends on the number of electrons that it contained. In other words, if an oil droplet contained more electrons, then it will have a greater negative charge. But whatever the charge is, it has to be a multiple of a small number, and that small number is due to the charge of a single electron. Using this interpretation, Millikan found the smallest difference between the droplet's charge. So by looking at this diagram of sample results, if we can find the difference in charge between oil droplets, that corresponds to the smallest value that the charges were a multiple of. And if we can find this smallest value, we can then find the charge of a single electron.
We have learned a lot from experience about how to handle some of the ways we fool ourselves. One example, Millikan measured the charge on an electron by an experiment with falling oil drops, and got an answer which we now know not to be quite right. It's a little bit off because he had the incorrect value for the viscosity of air. It's interesting to look at the history of measurements of the charge of the electron after Millikan. If you plot them as a function of time, you find that one is a little bigger than Millikan's, and the next one's a little bigger than that, and the next one's a little bit bigger than that, until finally they settle down to a number which is higher. Why didn't they discover that the new number was higher right away? It's a thing that scientists are ashamed of, this history, because it's apparent that people did things like this. When they got a number that was too high above Millikan's, they thought something must be wrong, and they would look for and find a reason why something might be wrong. When they got a number closer to Millikan's value, they didn't look so hard, and so they eliminated the numbers that were too far off, and did other things like that. We've learned those tricks nowadays, and now we don't have that kind of disease. But this long history of learning how not to fool ourselves, of having utter scientific integrity is, I'm sorry to say, something that we haven't specifically included in any particular course that I know of. We just hope you've caught on by osmosis. The first principle is that you must not fool yourself, and you are the easiest person to fool. So you have to be very careful about that. After you've not fooled yourself, it's easy not to fool other scientists. You just have to be honest in a conventional way after that. I would like to add something that's not essential to the science, but something I kind of...
So this is the view through a Millikan apparatus. There isn't much to see right now as there aren't any droplets in the system. So how about we introduce it? And now we see an entire star field of oil droplets. And you'll notice that they're all falling, and that's because they're all being pulled down due to the presence of the force of gravity. And that is it. However, if I turn on the E-field plates, you'll notice about half of them are traveling upwards, and half of them are traveling downwards. Moreover, if I flip the polarity around, they'll reverse in direction. So why is that? Why are half of them going up and about half of them going down? I'll let you think about that.